Okay, so we've got this sort of upside down ice cream thing here. The cone's made of copper. The hemisphere is made of something else. And we're given some information about the density of copper, and we're told the total mass and the total volume of the entire solid. And we need to work out the density of the hemisphere. What we can do is work out the volume of the cone and the volume of the hemisphere, and we can get a ratio. And we can use that ratio to split this value here of the total volume of the solid. So that means we'll know the exact volume of the cone and get rid of those x's. Once we've got the actual volume of the cone, we can use this information to get the actual mass of the cone. Once we've got the actual mass of the cone, we can take it away from this value to get the actual mass of the hemisphere, and then we'll have the mass of the hemisphere and the volume of the hemisphere. And since density is mass per unit volume, we'll just express one over the other and simplify, and we'll have the density of the hemisphere. So that's the plan. So the volume of the cone, and I've pasted in this here from the formula sheet, is equal to 1/3 pi r, which is x, so x squared, times h, which is 5x, and that's equal to 5/3, because we'll multiply by the 5/3 of pi x cubed. Volume of the hemisphere, excuse me. Well, the volume of a sphere is 4/3 pi r cubed. That's on your formula sheet. We only want a hemisphere, so we want half of 4/3, which is 2/3 of pi r cubed, but r is x, so x cubed. So the volume of the cone's 5/3 pi x cubed, and the volume of the hemisphere is 2/3 pi x cubed. So there's a 5:2 ratio in terms of the volume of the cone and the volume of the hemisphere. So as usual with ratios, that means there's 7 parts. 5 of them go to the cone, 2 of them go to the hemisphere. So that's 5/7 of the total volume goes to the cone, and 2/7 of the total volume goes to the hemisphere. So we can now write that the the volume of the cone here is equal to 5/7 of 504 pi centimeters cubed, and for the hemisphere it's 2/7 times 504 pi centimeters cubed. And there's enough working there, even though that's very tersely done, and I've done it because there's actually more space than I thought. That's enough information and enough working there for you to pick up the marks. So now that we've got the volume of the cone and we've got the density of copper, because it's made of copper, we can work out the mass of the cone. So the mass of the cone is equal to the volume of the cone times 9 grams. Why is it times? Well, for every centimetre cubed, we get 9 grams of mass. So that's going to equal 5/7 times 504 pi times 9. And the mass, therefore, of the hemisphere is equal to the rest. So it's 4752 pi grams minus the mass of the cone, which we've written above there. Now, we've got the volume of the hemisphere and we've got the mass of the hemisphere. And I can just put those into an expression now and stick them in my calculator. And I'll get it right. Now, I can simplify it. I could have written lots of sort of intermediate values here, working stuff out. I could try to get some value for this, but I'd end up with an approximation because either that or I'd write lots and lots of digits from my calculator. I don't see that there's a necessity to do that. So I'm just going to go ahead and say that the density of the hemisphere is equal to the mass of the hemisphere over the volume of the hemisphere, and that's equal to 4752 pi minus MC, which is this value here. So that's 5/7 times 504 pi times 9, and that's divided by the volume of the hemisphere, which is this one, and that's 2/7 times 504 pi. And I'll try sticking that in my calculator and see if we get anything good. So we've got a fraction. We've got 4752 pi minus another fraction, 5/7, and then we are multiplying by 504 pi and multiplying that by 9, and then on the bottom we've got another fraction which is 2/7, and we're multiplying that by 504 pi, and that gives me a value of 10.5. So 10.5 grams per centimetre cubed. So it's really just a question of going carefully and just working out the things you need to work out. I suppose you could go wrong by thinking, because you've got a ratio of 5:2 of the volume of the cone to the volume of the hemisphere, think that the mass splits by the same ratio. It doesn't, because it's made of something else. So if you had a hemisphere that was half polystyrene and half lead, then yes, there'd be 50-50 as far as volume is concerned, but they certainly wouldn't be 50-50 as far as mass is concerned. So you've got to be a little bit careful there. It's really this information here that allows you to work out the actual mass of the copper, and then you can take that away and get the actual mass of the hemisphere.